Ladies and gentlemen, welcome. Welcome to the design presentation of Delft Hyperloop 7. Partners, alumni, friends, family, and my dear team. Welcome. My name is Umika Bagole, and I am the team captain of the 7th Delft Hyperloop team. As team captain, it is my honor to lead this amazing team towards reaching our common goal. It is my job to create an operating environment in which every individual team member can perform optimally and work well together so that we, as a team, can reach our full potential. Together with our project manager, Pepijn de Kruijf, and our chief engineer, Guillermo Van, we form the management of this team. And tonight, it is our pleasure to show you what we have been working so hard on for the past 6 months. But before we get into that, I would like to take you back. Take you back to the early days of transportation. The history of transportation is a history of technological innovation. Technological revolutions in transport powered a next great leap in our society. For centuries, people have been asking themselves, how can we travel a longer distance in a shorter amount of time? To travel faster and easier, people rode horses, invented the wheel, and built boats. In the 19th century, the steam engine was applied to boats and trains. This completely revolutionized transportation. It allowed for faster, more efficient traveling over longer distances, and it enabled the expansion of trade, commerce, and communication between regions and countries. Still, air travel was inconceivable for many years. The thought of flying seemed unnatural and scary. People couldn't believe that humans could fly with machines heavier than air. Except for a few pioneers. The Wright brothers kept asking themselves that age-old question. How can we travel a longer distance in a shorter amount of time? The Wright brothers believed they could fly, and in the beginning of the 20th century, they flew. They had successfully invented the world's first airplane. Traveling by airplane connected people and cultures across the globe. And today, air travel is the most commonly used mode of transportation for long-distance traveling. Back then, these ideas might have seemed crazy or even impossible because they challenged the world that people were used to. But it were these unconventional and radical innovations that made it possible for us to connect the world, to bring distant cultures together, and to expose us to new ideas and new understandings. Every technological innovation powered a next great leap and shaped the society that we know today. Because after many decades, we still use these modes of transportation. Let me take you on a journey of what traveling looks like today. So recently, I've been looking into going on a nice city trip in Europe for the summer. Just a short and relaxing breakaway after a year long of hard work at Delft Hyperloop. And I thought about going to Milan, one of the most beautiful cities in Europe. And I was facing a dilemma. It is a dilemma you may recognize. We want to travel, explore, and connect, and we want to do this in a fast and comfortable way. But with climate change being one of the biggest challenges that we as humankind have faced yet, we want to do this in a sustainable way. And traveling by train is the most environmental friendly for my trip to Milan. But door to door, this will take me around 16 hours and 4 to 5 transfers on the way. That doesn't really tick the fast and comfortable box. So I started looking into flying. And this would only take me 1 hour and 40 minutes. Seems attractive, right? But with all the time that I will need to go to the airport, wait for my flight to take off, and then go from the airport of Milan to the city center, this trip would still take me around 5 hours. And then, I haven't even mentioned the amount of energy that this flight would consume, which is more than 13 times as much as traveling by train. Quite a dilemma. There seems to be no ideal way for us to travel. So, once again, we've come to a point where we're asking ourselves a question. And it's that same age-old question that people have been asking themselves for centuries long. But with the transportation sector being one of the biggest contributors to climate change, we've added a new challenge to the equation. The question we're asking ourselves now is, how can we travel a longer distance in a shorter amount of time in a sustainable way? We at Delft Hyperloop have the solution for you. And just like the train, the boat, and the airplane, this idea may sound unconventional, radical, or even crazy. Because yet again, we are challenging the world that you are used to today. But with the current challenges that we as a society are facing, we now, more than ever, need to explore these ideas that might seem unconventional, radical, or even crazy. And Hyperloop is such an idea. It is a solution, a new mode of transportation that can reach speeds of 1,000 kilometers an hour in a highly energy efficient way. But how does it work? And why is it so hard for the current modes of transportation to reach such high speeds? First of all, this has to do with air drag. Air drag increases not only linearly, but quadratically, meaning that if you want to double the speed of a current mode of transportation, such as a car, you will need 4 times as much energy. What a Hyperloop does is it limits this factor by moving the pod, we call the vehicle a pod, through a tube in which there is a near vacuum environment. This makes the pod encounter very little air drag. The second major limiting factor that the current mode of transportation encounter is rolling resistance. And rolling resistance also increases with speed, making the, for example, wheels of a current mode of transportation to become very inefficient at higher speeds. Hyperloop eliminates this problem by using electromagnetic forces to levitate the pod, making it not touch the tube at all. To move forward, a Hyperloop also makes use of magnets, which provide a contactless magnetic propulsion. By limiting the drag and friction, A Hyperloop can reach speeds that come close to the speed of sound, using only very little energy. Every couple of minutes, a Hyperloop pod will move from one heart of a city to another, providing a solution to long and uncomfortable travel hours and enabling the energy transition. This completely revolutionizes mobility as we know it today. So let's put this new mode of transportation into perspective and see how traveling with a Hyperloop would work out for my journey to Milan. First, we go to a centrally located Hyperloop station, say here at Rotterdam Central. There, we board a Hyperloop to Milan, and in less than 1 hour, we arrive at station Milano Centrale, right in the city center of Milan. A journey that is around 3 times as fast as the current journey with the current most fastest mode of transportation, and uses only amount the same energy as a train. Instead of making concessions between speed or energy consumption, a Hyperloop provides us with a solution. It allows us to travel, explore, and be more connected than ever. And it makes all of this possible in a fast, comfortable, and sustainable way. But how did this futuristic concept come to life in Delft? In 2013, Elon Musk gave an impulse to the realization of Hyperloop when he wrote a white paper about it. Shortly after, he announced the Hyperloop SpaceX competition in Los Angeles. And this inspired a group of TU Delft students. And of course, they wanted to be part of this challenge and compete in this new competition with a new concept. They recruited more talented, motivated, and ambitious students and became a team. Delft Hyperloop was born.
Coming and participating in an incredible event.
And that's Delft.
And the award goes to Delft Hyperloop.
A history full of incredible achievements, where we, as Delft Hyperloop, are all so proud of. Delft Hyperloop 1 competed against over 200 student teams and took home the very first prize at the very first edition at the Hyperloop SpaceX competition, putting Delft Hyperloop on the chart worldwide. The next years, Delft Hyperloop 2 and Delft Hyperloop 3 also competed at the Hyperloop SpaceX competition, which shifted its focus towards speed. However, for Delft Hyperloop 4, there was no SpaceX competition. So this team decided to take matters in their own hands, and they went for a record attempt. With their pods, they were able to reach an incredible speed of 366 kilometers an hour. Delft Hyperloop 5 was the first team to compete at a new and totally different competition, the European Hyperloop Week. This competition challenges student teams to not only build a Hyperloop prototype that works on a small scale, but to develop the best Hyperloop cutting-edge technology that can be applied to a real-life Hyperloop network. This competition also challenges student teams to research the current and future challenges ahead for the implementation of a Hyperloop infrastructure. Our immediate predecessors, Delft Hyperloop 6, made a major step towards a scalable Hyperloop system with their design, Helios I. For the first time in Delft Hyperloop history, Delft Hyperloop 6 managed to build an active vertical levitating pod. And their design was upside down, which made it more stable and energy efficient. With this hanging system, Helios I stood apart from all other designs at the competition. With Helios I, Delft Hyperloop 6 took the lead and won the Complete Pod Design Award at the European Hyperloop Week of 2022 on home ground. A legacy where we at Delft Hyperloop are all so proud of. A legacy we build upon, and one that inspires us to take the next steps. And now, it is time for Delft Hyperloop 7 to accelerate. And I know that this idea of a levitating capsule traveling to a low-pressure tube might still sound a bit crazy to some of you. And I have to agree. For the realization of such a system, a lot still needs to be done. The boundaries of technology will have to be pushed, and the socio-economic and technical feasibility of such a system will have to be explored. But that is exactly what we do here at Delft Hyperloop. And for that, you need a team. A team consisting of people crazy enough to explore the potential of this unconventional idea. A team that dares to take on a challenge to design, build, and demonstrate Hyperloop technology in just 1 year. And that is the team that I am so proud to present to you tonight. Delft Hyperloop 7 consists of a group of people with 10 different nationalities, 13 different study backgrounds, and in total, 41 different personalities. We started off our year as strangers to each other, with our own interests, our own backgrounds, and our own motivations to join this team. Some of us really wanted to put our engineering skills to the test and become a top-notch engineer. Others wanted to develop their soft skills and learn to communicate and work well together in such a big and multidisciplinary team. But all 41 of us were united by one mission. A mission that defines our reason why. And this mission is to catalyze the implementation of the Hyperloop system by demonstrating its full-scale potential. By showing the world that the technology that this team develops can be applied to a real-life Hyperloop network, and by finding solutions for the current and future challenges ahead for the implementation of a Hyperloop system. We, as Delft Hyperloop, are accelerating the implementation of Hyperloop. So, we have a mission. But how do we contribute to this in just 1 year? How do we show the world what the potential of Hyperloop really is? To us, the answer was clear. By competing at the biggest Hyperloop competition out there, the European Hyperloop Week. This year, day in and day out, we are working towards July 2023, when we will be competing at the European Hyperloop Week in Edinburgh, against student teams from all over the world. To go into this competition, we needed all of our noses pointed to the same direction. So, we set up a goal. And our goal is to win at the European Hyperloop Week of 2023. An ambitious goal. But a challenge is what we like here at Delft Hyperloop. Most of us are putting our studies on hold for 1 whole year to voluntarily dedicate ourselves to this project and this team. And we do not get paid to do this. We do not get any study credits for our work. Yet, we put in our heart and soul into this project. A dedication that often includes long hours and putting in that extra effort. And this team does not strive to perform well. We strive to perform incredible. We do not strive to be just good. We strive to be at the top of the game by doing what might seem impossible. And with this goal, a group of people that started off as strangers to each other quickly became a high-performing team. A group of individuals, or maybe better said, a group of friends, who work together towards a common goal and who consistently perform at a level that exceeds expectations. With this team, united by one mission and striving for one goal, we, as Delft Hyperloop 7, are ready to accelerate. To reach this goal of winning the European Hyperloop Week, we set up a winning strategy. I would now like to give the floor to our project manager, Pepijn de Cruijff, who will tell you more about how we are working towards this goal.
As the 7th Delft Hyperloop team, we set out to catalyze the implementation of the Hyperloop system by winning the European Hyperloop Week 2023. Within 10 months, we have to design and build a completely operational Hyperloop prototype. And the constraints we face in this are unlike many other projects. Take, for example, the James Webb Space Telescope. As many of you probably know, this stunning piece of engineering made its way to orbit last year. and took the most remarkable images of our universe. The resulting pictures are sharper and more stunning than anything what scientists have been able to capture before. And while this project proves what man is capable of when all efforts are bundled, it did not really go according to plan. It was approved in 1999 for a potential launch in 2007 with a budget of $1 billion US. However, endless delays and setbacks plagued the program. In the end, the telescope was launched in 2021, costing $10 billion US in total. That is 14 years later than originally planned, 900% over budget. And this is a recurring pattern. In fact, I could stand here all day naming examples from recent history. Not only the James Webb Telescope, but also the Joint Strike Fighter or the new Tesla Roadster. As it turns out, engineering is hard. Especially engineering something that has never been done before. Now, of course, what we do at Delft Hyperloop is not of the same scale as the James Webb Telescope. However, we face some of the exact same challenges as these projects do. We are building something that has never been built before, and just like these projects, we face many unknowns along the way. However, for us, unlike these projects, going over schedule or going over budget is not an option. Our competition will take place from the 17th to the 23rd of July, whether our prototype is ready for it or not. And we have to get there with the resources we have. My name is Pepijn de Kruijf, and I'm the project manager of Delft Hyperloop. It's my responsibility to allocate the resources we have as efficiently as possible, whether that's the time of our engineers or the resources that we get from our partners. Getting to the EHW, both in time and within budget, will be one of the biggest challenges we have this year. And today, I would like to show you the journey that we undertake to get there. And to have a fully operational Hyperloop prototype, by the time of the competition, we've split up our year into 4 phases: the design phase, the production phase, the testing phase, and the competition itself. During the design phase, we completely design our pod from scratch. We start out with multiple concepts on a whiteboard and iterate over these until we have a full 3D model of our pod. Once we're finished with design, we move on to production. And we do that here, in the Dream Hall. And this is a meticulous process because all designed parts need to be produced by hand within minimal tolerances. Here you can see Massimo producing one of this year's first parts for the chassis. And once we're done with production, we move on to testing. And as you maybe can imagine, we start out with testing little things, like whether a part can sustain the loads that it's exposed to, or whether it can operate in a vacuum. But once entire subsystems, like the batteries or the brakes, are fully operational, it's time for the next step, their integration with other subsystems in the pod. At this point, all the different subsystems in the pod come together. The engineers, having spent months on designing, building, and testing their own subsystems, now have to make sure that it works well with other components in the pod. And this is the riskiest phase. Because if something goes wrong here, we have to restart the design cycle. This means that we have to redesign, then produce, and then test the part before knowing if the replacement does actually work. And this is exactly why it takes professional engineering companies, like car manufacturers, often multiple years to develop a product. Unfortunately, we don't have that kind of time, making it so important that our design is correct the first time around. If everything works and all subsystems operate seamlessly with each other, we're ready for the competition. To compete in the EHW, we have to ship our pod and about 13 tons of steel for our track to Edinburgh in Scotland. And here we have to rebuild our 50-meter track and align it onto millimeters in time for the competition. And then we have 1 week to prove to the jury of the competition that our pod is the best. These 4 phases are the steps that this team needs to take to accomplish our goal. 10 months of hard work and complete dedication by everyone in the team. At this point, we're about halfway there. We've been working on this project for 6 months, and we're here today to celebrate the successful completion of our design. But before showing you the design that our engineers worked so hard on, I would like to shed some light on how we got there. And to start, let me take you back to the first days we spent together as a team. It was in a little town in Brabant called Windhelre. At the start of this weekend, we were just a group of 41 students that decided to commit themselves to this project. And we spent the weekend on getting to know each other, the team that we would work with for a year. And during this weekend, we set the goal of winning the European Hyperloop Week 2023. Setting a goal, however, is not the hard part. The hard part is actually accomplishing that goal. After all, we were just a group of 41 students, and no one of us had any experience in building something like this. And the Monday after that first weekend in Brabant marked the start for everyone to start working towards our common mission within their speciality. We formed 7 departments, each of which with their own critical function within the team. First, there's the levitation department. It's their responsibility to make sure that our pod levitates, an essential characteristic of a Hyperloop pod. But once you're levitating, you're not there yet. Now you need a motor to propel yourself forward over the track. This is the responsibility of the propulsion department. These subsystems are mounted on a single body, what we call the chassis. The chassis, together with the track, the brakes, and the aero shell, are the responsibility of these people, the mechanical department. The sense and control department links together all these different subsystems electronically and controls them from a central place. It's also their responsibility to provide the subsystems with the power they need. And then we have a mechanical department. A business department. Our business department maintains contact with our partners and convinces the public of our story. And the design engineers play a critical role in this by making the Hyperloop concept understandable through beautiful visualizations and design. And then finally, we have a scalability department. And this department is what makes this team truly unique. They look further ahead than the prototype that we developed this year and instead focus on the challenges that a Hyperloop system faces when scaled up to transport a large amount of people between countries. And they do this by writing a socio-economic and a technical research paper. And this year, the socio-economic paper goes into detail about the social acceptance of the Hyperloop infrastructure. As you maybe can imagine, the construction of large tubes through the landscape could meet some resistance by the public. They conduct research on which design configuration would minimize this resistance. The technical paper the scalability department is writing looks at possible thermal management systems for full-scale Hyperloop pods. And this is a really challenging problem that our engineers actually encountered themselves this year. So at this point of the year, We knew the steps that we needed to take to get to the EHW, and we had set up the departments within our team to get there. Now, it was time to start working on a conceptual design. As you can imagine, there are many possible design configurations for a Hyperloop pod. And because Hyperloop is a relatively new concept, there is no consensus between student teams or companies on which design is optimal. To create a conceptual design, we had to devise a vision of what a future Hyperloop system would look like and how we as Delft Hyperloop can lead the way in realizing this future. And we decided on 3 major improvements. The first step Delft Hyperloop is taking this year is that of full levitation. As Umika explained earlier, levitation eliminates friction, allowing for more efficient guidance over the track. And last year, they took the large step of starting to vertically levitate over the track. However, their pod still made use of wheels to guide the pod on the sides. This year, we continue the development of the levitation system by adding lateral modules. And these lateral modules use active magnets to guide the pod on the sides. And together with the vertical system, it makes sure that our pod does not make any contact with the track during operation. And then secondly, we decided to develop a new kind of motor. And to understand this decision, you have to know what type of motor our predecessors made. They implemented a linear synchronous motor. And this motor makes use of coils installed over the entire length of the track. And by letting current run through these coils, a magnetic field is created, propelling the pod forwards over the track. You can compare this type of motor to a conveyor belt, transporting passive elements over a motorized track. And this makes the pod itself lighter and simpler, compared to a design where the motor is within the pod. However, there's one major disadvantage, though, with an on-track motor. Because it requires coils and other expensive electronics installed over the entire length of the track, the material and financial cost scale significantly with the length of the infrastructure. And this is fine if you have a 50-meter track like us, but not if your infrastructure spans hundreds of kilometers, as this would require an enormous amount of precious materials, like copper, making it far from a sustainable solution. We decided to develop a new kind of on-pod motor. This is truly a one-of-a-kind motor, having never been built anywhere in the world at the scale that we do so. It allows us to reach extremely high efficiencies. And because it sits inside the pod instead of inside the track, it greatly reduces the cost and environmental impact of our infrastructure. We closed off conceptual design, deciding that levitation and propulsion would be the 2 areas that we would improve on the most this year. And we moved from conceptual design to detailed design, fully working out all design elements of our pod. But during a Hyperloop year, many challenges come up that you didn't plan for originally. And these challenges force the team to remain flexible, as delays are not an option. And one of these challenges was that of heat generation. You see, the components critical for the motor that we moved from the track to inside the pod cannot operate in a vacuum. And because our pod is supposed to travel through a vacuum tube, this would not work for us. And to fix this, our engineers placed these components in an air-sealed compartment, what we call a vacuum box, where atmospheric pressure is maintained, even though our pod is in a vacuum. Very late in the design process, however, we found out that these components, critical for the motor, generated a lot of heat. And because they're stored in a sealed compartment, there's nowhere for this heat to go. Unlike a car or computer, we do not have the option to dissipate this heat away to surrounding air, because our pod is in a vacuum. And radiating the heat away is also not an option, because the surface area of our pod is not large enough for this. So at this point of the design process, we hit a dead end. And we had two options. The first was to remove the vacuum box altogether and let outside air cool these critical motor components. However, this would lead to our pod not being vacuum compatible anymore, which is an essential part of a Hyperloop system. The second option we had was to do anything we could to develop a vacuum-compatible thermal management system. But this would be very risky, as we were already nearing the end of the design phase, and we did not know whether such a system would even be possible. But the team came together and chose the second option, to try anything they could to solve the heat generation problem. And this would mean that our year would be even harder. But the team decided that if everyone put their shoulders in, we would be able to solve it. We formed an 8th department, the thermal management department, consisting of these 3 people. They left their old department to start working on a challenge which has not been solved before in our history. And I'm happy to say that they found a solution. They designed a system which is able to capture the heat that's generated inside the vacuum box and store it for the duration of the run. And this system allows our components to remain cool and proves this system as a solution for full-scale Hyperloop pods. These 3 innovations, full levitation, a new highly efficient on-pod motor, and a vacuum-compatible thermal management system are huge steps and prove what this team is capable of. It's the dedication of our engineers what makes it possible for us to be here today and celebrate the successful completion of our design. A design we believe is an important step towards the future implementation of a Hyperloop system. A design we believe will win the European Hyperloop Week 2023. Ladies and gentlemen, I'm beyond excited to show what we've been working on these past few months. This is Helios II.
For years, society has settled on boats, trains, cars and airplanes. The demand for fast and efficient transport continues to grow enormously. However, the current modes of transportation play a significant role in the pollution of our environment. So, in terms of traveling fast but in a sustainable way, time has been standing still.
I believe that the world is ready for a fast and greener mode of transportation. By solving unexplored challenges, I want to bring the full-scale Hyperloop system closer to becoming a reality.
This year, I want to convince as many people as possible about the Hyperloop technology to create awareness for the transportation method of the future.
By creating the foundation of the pod, I contribute to a safe and functional Hyperloop that can perform at incredible speeds, allowing me to push the boundaries of technology.
The challenge of realizing full magnetic levitation is a crucial element of the Hyperloop system, so I'm happy to be part of Delft Hyperloop to work on this.
Linear magnetic propulsion is still on unexplored grounds. This year we take the unique chance to boldly go where no one has ever gone before.
I want to test myself as an engineer by creating a thermal management system in a vacuum environment, which is one of the Hyperloop's largest technological challenges.
The sense and control systems form the heart and brain of the pod. It thrills me that advances made here will trickle down to all other systems and allow them to perform at their best.
The world is ready for change, and Delft Hyperloop is ready to take on the challenge to sustainably revolutionize the way we move. Now is the time to accelerate. We are Delft Hyperloop 7. And this is Helios II.
Incredible. I think I'm not the only one that gets goosebumps when looking at this design. Every time I see it, it makes me extremely proud of what this team has achieved so far. My name is Guillermo Van, and I'm the chief engineer of this year's Delft Hyperloop team. As the chief engineer, it is my responsibility that all systems work perfectly together, resulting in an optimal performance at the European Hyperloop Week in Edinburgh. Tonight, it is my honor to take you on a journey through the Hyperloop system that we have worked so hard on for the past 6 months. But before we dive into the technical details, I would like to show you something that can be seen back into every part of our design: the design values. Here at Delft Hyperloop, we have 3 design values, and together they form the foundations on which we measure the quality of our engineering. Every day, we ask ourselves the same question over and over again. Can we apply what we have designed to a large-scale Hyperloop network? That is why scalability is one of our most important design values. This is how we came to the decision to drastically change last year's propulsion system by building an onboard motor that keeps the infrastructure as simple as possible. Secondly, we want to be energy efficient. By building a levitation system, we're able to take away all rolling resistance that would be present otherwise. This is one of the many aspects that makes our design as energy efficient as possible. But we do not only want to be scalable and energy efficient. We also want to make sure that we have designed a system that can be operated in multiple environments, ensuring the robustness. Not only because we have to transport the entire pod and track to Edinburgh, but also to show that our design is not constrained by the environment it operates in. That is why every single component is designed to withstand a wide range of operating conditions and is tested extensively. With these 3 design values, we were able to actually make a design that contributes to our goal of winning the European Hyperloop Week. Let's now take a closer look into every single subsystem of our design. We will start with the levitation system. This year, we have set the ambitious goal of full levitation. It means that we do not want to touch any part of the track at all times. The levitation system does this by magnetically suspending the vertical motion as well as the lateral motion of the pod. But how do we do this, and what makes it so difficult? In order for us to design the levitation system, it is crucial to first know the configuration of the pod with respect to the track. It has been decided to build further on last year's configuration, where the pod is riding under the track instead of above it, like a conventional train. This results in an inherently stable system where a small disturbance on the pod will result in it wanting to balance back to its original position. So, now that we know that the pod is under the track, let's take a closer look at one of our vertical levitation modules. This is called a hybrid electromagnetic suspension module, or HEMS module, due to its hybrid use of permanent and active magnets. The permanent magnets are placed on a so-called iron U-core that are able to guide the magnetic field lines very efficiently. Because the track above it is made out of ferromagnetic steel, the modules attract themselves upwards to the track. We're now sticking to the track, but we want to levitate. So how do we get off it again? We do this by placing coils around the poles of the permanent magnets. By letting a current flow through these coils, an active magnetic field that opposes that of the permanent magnet is created. This way, we're getting off the track again. By measuring the distance to the track and changing the flow of the current 6,000 times per second, we're able to keep the entire pod level midair. 4 of these vertical levitation modules are placed on top of the pod, and together they're able to carry the entire weight of the pod. But we're not there yet. We also want to make sure that the pod does not touch the track in the lateral direction. So for this, an electromagnetic suspension module, or EMS module, is developed. Unlike the HEMS modules, the EMS modules only contain active magnets. This means that the magnets will only attract themselves towards the track when they're turned on. But how do we control this lateral suspension using these modules? Well, there are 2 ways you can go in the lateral direction, either to the left or to the right. When the distance from the pod to the track on one side gets too small, the opposing EMS module will become active. This way, the pod will balance back to its original position without touching any part of the track. 4 of these EMS modules are placed on the side of the pod in order to constrain all possible rotations. We are now fully levitating, and we have full control over the entire orientation of the pod. A crucial step towards a complete Hyperloop system. But we're not there yet. We do not only want to levitate. We also want to find a fast and efficient way of accelerating our pod to its top speed. Since we're not touching any part of the track, we cannot do this by driving the wheels, like on a car or a conventional train. So for this, we use a so-called linear magnetic motor. The propulsion department is responsible for developing this motor to propel our pod forward, backwards, and brake regeneratively only using magnetic force. There are many linear motors to consider, but after weeks of research and extensive analysis, we found the optimal motor for our design. We chose the linear flux switching permanent magnet motor. What a mouthful. This motor showed a very promising performance on paper, but it was still a huge risk that we took. That is because we're dealing with a motor that has never been built before anywhere in the world at this scale. Anywhere in the world at this scale. So, how does this motor work? And why is it worth the risk? Well, the motor consists of 2 parts. One part is mounted on the track and is called the stator, and the other part is mounted on the pod and is called the mover. The steel stator hangs over the entire 50 meters of the track and weighs about 3 tons. about the same weight as a white rhinoceros. 700 steel teeth stick out of this stator, and they're all aligned within a 2 mm accuracy. You can only imagine the amount of precision that is required when producing and assembling this system. And then we have the mover. This is the place where all the magic happens. Just like the levitation system, also the mover consists of permanent and active magnets. These magnets attract themselves towards the steel stator, but this attraction is controlled in a very clever and precise way. This attraction is controlled in a very clever and precise way. When one of the magnets of the mover arrives at the tooth of the stator, it will be turned off. It is exactly this moment when another mover that is not under the tooth of the stator will be turned on. This way, the mover snaps towards that next tooth. By repeating this cycle over and over again, we're able to create a forward motion. We have now full control over the motion of the pod without touching any part of the track. A difficult idea that we had to figure out from scratch. Such a complex motor has many parameters to consider. But after months of research, back-of-the-envelope calculations and simulations, the optimal combination of all these parameters was found. We managed to make a motor that has a top speed of over 10 meters per second while having an energy efficiency of over 93%. An incredible achievement at the very end of the design phase. One last thing about our motor. Not only does it generate a force forward, but it also lifts the pod upwards. In fact, this lifting force is so high that it can carry about 40% of the entire weight of the pod. This means that the propulsion system actually helps the levitation system in carrying the pod. This integration between these two critical subsystems is something that has never been done before in the history of Delft Hyperloop, and that is at the frontier of cutting-edge Hyperloop technology. As you could imagine, we have a lot of electrical components on board. But unfortunately, a lot of these are not compatible to a near vacuum environment that our pod should be able to operate in. That is why they're kept safe in a so-called vacuum box, where the pressure is kept at atmospheric conditions. This vacuum box consists of a carbon fiber shell that is capable of bearing the loads of a pressure difference while being as light as possible. It is a prototype of what on one day will be the capsule that could carry passengers to their destination. When designing the vacuum box, we stumbled upon a problem. As Pepijn mentioned before, the motor drives that are kept in it generated too much heat during the run. In fact, one of the motor drives had a power loss of almost 700 watts. That is about the same heat that comes from a terrace heater. So when we saw these numbers, we became, of course, very worried. But the thermal department quickly came to a scalable and robust solution. They decided to build a so-called heat battery, where all the heat could be stored, taking it away from critical components. Let's take a closer look into how this is done. First, the heat from the motor drives will be blown away using fans. When the hot air arrives at the heat battery, aluminum heat fins will guide the heat to the core of the heat battery. Within this core, a phase-changing material, or PCM, is stored. This is a type of wax that melts at a certain temperature, just like the wax from a candle. When this PCM melts, it's able to absorb more and more energy while keeping the temperature constant. This is exactly what needs to happen in the vacuum box in order to keep the temperatures low. A simple solution in order to protect our most complex systems from overheating. We've now come a long way, but we still need all subsystems to communicate with each other and get power. This is done by the sensor control department. They are the brains and heart of the pod. In order for all subsystems to get power, a battery consisting of 672 vacuum-compatible lithium-ion cells is installed on the pod. In order to size this battery, we had to know two things. First, the amount of energy that needs to be stored in these batteries. With about 7 kilowatt hours of energy, our batteries will be able to perform the intended runs at least 3 times, ensuring the robustness of our system. Secondly, we needed to know the power, or energy per second, that our batteries should be able to deliver. With a stunning 82 kilowatts of peak power, our batteries will be able to accelerate the pod to its top speed while levitating. The eyes and ears of the pod consist of various sensors that are placed strategically. The most important one of these is the localization system. In order for the motor to operate correctly and efficiently, we need to know the exact location of the pod at all times. With the localization system that we have developed, we're able to know the location within a 3mm accuracy. This is done by mounting an encoder strip over the entire length of the track. An onboard laser will read off this encoder strip and count the stripes. This encoder strip will give the pod information about the exact location, speed, and direction of travel. Various other sensors that monitor the exact temperature and pressure of subsystems are also installed on the pod. The onboard computer then reads out this data and can take decisions about the actions that need to be taken completely autonomously. This data is then sent over to the ground station, where we can analyze it and learn more about our pod every day. And we have now arrived at our last subsystem. Now that almost everything is finished, it is time to keep it all together while maintaining structural integrity. This is done by the mechanical department. They are responsible for the track, emergency brakes, aeroshell, and chassis. In order to guide the pod and actually reach high speeds, a long track will be brought to Edinburgh as well. This track consists of a total of 140 steel I-beams, altogether weighing over 8 tons. This colossal structure will span over a length of 50 meters. And to put that into perspective, that is more or less the length from this stage all the way to the last row and back. So the track is very long, but it's not infinite. So what do we do when we reach the end of the track and suddenly our motor fails? For this, a pneumatic emergency braking system is installed on the pod. This system uses 4 braking calipers that uses springs that extend outwards to the track when needed. The generated friction force is then so high that it can bring the entire pod to a standstill within half a second. On top of that, when the power on the pod is lost, or the pressure in the tank is lost, the brakes will immediately extend outwards to the track. This ensures the safety of our system, even if everything fails. And then we have the aeroshell. This 3.5 meter long carbon fiber housing is there to protect all of our subsystems while having a shape that is as aerodynamic as possible. Together with the design engineers, the mechanical department found this optimal shape around all of our subsystems. And then last but not least is the backbone of our pod, the structure where everything will be mounted on, the chassis. Because everything needs to be on the chassis is one of the first things that we have produced so far, and I'm beyond excited to already show you this design in real life. After various iterations, this optimal configuration came to life. It is designed to withstand the high loads induced by the propulsion and levitation system, while being as light as possible. It is a double ladder frame consisting of aluminum beams. And as you can see, it is very easy to access every subsystem, making our design easier to operate and thus safer. And with that, our design is finished. By using revolutionary ideas to come up with innovative, cutting-edge technology, we are accelerating the implementation of the Hyperloop system. A scalable, energy-efficient, and robust product is what we will bring to Edinburgh to win the European Hyperloop Week. I would like to give the floor to our team captain, Umika Bagole, for some closing remarks. Thank you.
Isn't it unbelievable what this team has already been able to accomplish in under 6 months? This year, we aim to design, build, and demonstrate the best Hyperloop pod a student team has ever developed. But we do not want to keep our story to ourselves. We want to reach a greater audience, to show them what a year at Delft Hyperloop really looks like, and to inspire them to accelerate together. That is why we are making a documentary of our year, and that is also why you've been surrounded by so many cameras tonight. So, before you continue on to the drinks after this presentation, I would like to ask you to take a look at the flyer that was given to you, and see how you can support the realization of this documentary. Tonight, we have shown you our final design. With this design, we are taking a major leap towards a scalable Hyperloop system. Helios II will be fully levitating, will be propelled by a new, never before performed and highly energy efficient motor. And it will be doing all of this while being fully vacuum compatible. With this design, we are one step closer to our journey to the European Hyperloop Week of 2023. But we're not alone on this journey. Our partners play an indispensable role in our success. And that is why I would like to take a moment to thank them. Our partners provide us with resources, whether that is financial support, materials, or knowledge or expertise. And their enthusiasm is what keeps this team going. I would also like to thank our alumni from Delft Hyperloop 1 to Delft Hyperloop 6, who even after their Delft Hyperloop year, continue to help us out with their knowledge and their experience. And not to forget, I would like to thank our family and friends who keep up with us and continue to support us towards reaching our goal, even though that has been meaning that they have been seeing us a little bit less. I'd like to thank everyone who has been involved with us in any way. Thank you for celebrating the final design, our Helios II. And last but not least, I would like to thank my team. Your tireless efforts is what makes all of this possible, and we couldn't have wished for any greater team. I'd like to ask you to come and join me on stage. Ladies and gentlemen, can I have a very big applause for Delft Hyperloop 7?